going to, swing away from the ruthenium and the ether is going to coordinate. And that's precisely what happens. And that's why these catalysts are even more active than the second generation Grubbs catalyst. So the funny thing is, you also have a generation 1 Hoveyda Grubbs and a generation 2 Hoveyda Grubbs. And here we have a nice comparison. Grubbs 1 is just our tricyclohexylphosphine. Grubbs 2 is with the N-heterocyclic carbene. And the same with the Hoveyda Grubbs. We have generation 1 with the tricyclohexylphosphine, and generation 2 is again with the N-heterocyclic carbene, which is going to do what? Sorry?
Trans effect.
Trans effect, yes. It's going to make that weak O ruthenium bond even weaker. And it's going to absolutely swing away in solution, and it's going to pick up an alkene, and you're going to get a metathesis. This is basically just something from the Department of Useless Information, basically how you make it. That's not so important. But anyway, this was made in 1999. So when I was a first-year university student, they reported this. And this is a very widely used catalyst for a range of metathesis reactions. So it's important, Grubbs 1, Grubbs 2, understanding why this is more active. Hoveyda Grubbs and Hoveyda Grubbs 2. In a way, Hoveyda Grubbs 2 combines both things. It combines the increased sigma donor strength of the trans ligand and coordination of a weak ligand. So this is a hot potato, right? Okay. What I want to talk about here, I mean, these are by no means the only variations. People have made lots of versions of Grubbs. Because you can play around with the substituents on the carbene. You can play around with the substituents on the phosphine, right? If you stick to the first generation system. You can play around with, the substituents. You can have different substituents. You can have bulky ones. You can have less bulky ones. You can have electron donating, electron withdrawing. You can do all sorts of things. Essentially, you can really modulate the steric and electronic properties at the metal center in a number of sites, right, as you can see here. For example, if we stick to the second generation Grubbs-Hoveyda system, you can also play other games, like replacing the chlorides with other anionic ligands. And that's precisely what they've done here, right? They've replaced it with this chelating group here. So you can modulate the electronic and sterics here, on the sides of the nitrogen, and of course here. You can also modulate this isopropyl group and, for example, replace it with something else. So that's what scientists have, of course, done, in an exhaustive way. In fact, every time you open Journal of the American Chemical Society, there's someone that has made some new version of the catalyst and shows that it's better, anyway. What's also interesting to see, however, is if you modulate the groups or the substituents and you tweak the electronic characteristics, as we see here, it also changes the selectivity of the catalyst. Now remember earlier in the presentation, we had this discussion about E and Z selectivity. And here you can see that you can play around with the EZ selectivity by changing the characteristics of the catalyst. And let's have a look at some of this data. Also the yields are highly affected by it, and the turnover frequencies and the turnover numbers and stuff like that. Here we're essentially doing a cross metathesis between this alkene and this alkene, and we end up with these two possible products. Now, what do you guys notice? Do you see anything? Well, you can see that you can swing the ZE selectivity from very much Z to very much, well, not very much, but more E.
But like C has a lot of selectivity.
Oh, sorry, yes. C, this guy. So let's try and rationalize that. Why is that? C has a very high E selectivity, and what has a very, 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 very high Z selectivity? I'd say B. So what is the difference between these two? Well, it's difficult because we've modulated two things, right? We've changed the substituent to an adamantile, which is very bulky, and we've changed it. So we can't really compare that because we've varied two things. But let's compare A and B, because in A, all I've done is I've modulated one of the substituents on the nitrogen. What happens? So there's A and B. Well, the problem is the catalyst loading is a bit higher, but that doesn't matter. This is the catalyst loading in mole percentage. But what happens? In A, we've got a very high, well, let's say a pretty high selectivity towards E. And in B, we've got a very high selectivity towards Z. But what is the only explanation for that? Well, it must be because in B we have this very bulky substituent here, the adamantile group, and that's going to result in the fact that the alkene can approach the ruthenium center only in a conformation that's going to result in a minimization of steric pressure.
So we come from the left, yeah?
It's going to come from below. It's going to come from below, remember?
Substituents downwards.
But the substituents are going to be pushed downwards because of this very bulky adamantile residue here. And that's going to steer the selectivity in a different direction. So you modulate the selectivity by modulating the ligand. Anyway, that's just to show you how you can really fine-tune selectivities in cross-metathesis, but also activities. Remember in the first lecture I said it's always activity and selectivity. And this is an example of where you can very nicely see that. And the same thing for C and D, right? Do we have the same trend? Well, yes, we do. For C we have a skewed selectivity towards E, and for D we've got well, it's not really, I would say, a very useful data point because the yield is less than 1%, so it's a very inactive catalyst, which is quite interesting, I think. But you see, another interesting thing is just by replacing the chlorides with these guys here, really skews dramatically the activity as well.
Does that mean that D is less active because it has that really bulky group on the top?
No, I don't think so, because in B you've also got that bulky group, and it's got okay, at a 5 mole % catalyst loading, it's got a yield which is, okay, it's not great, but it's about 64%. So apparently, the conclusion is that this, replacing the chlorides with this substituent here also somehow seems to enhance the catalyst activity, apparently.
Is it that resonance maybe?
Well, yes, it seems to somehow potentially, it could stabilize the one of the intermediates, I think. But I think that's really sort of all for now, yes.
Isn't like time in minutes like time for such a yield to be obtained? Or not?
So reaction.
It's the reaction
Right.
time.
So like if a smaller reaction time would be better than the last one, right?
Yes,
So
indeed,
CM would be
indeed.
better?
But so the reaction times are different. That's true. So you have to take that into consideration. See, I mean, if you compare, if you still make that comparison between, let's say, B and D, I mean, the comparison still holds regardless, because you've got less than, even though you've only done the reaction for 30 minutes, you've got less than 1% yield. Okay, you could extend that reaction time by 4. I doubt you're going to get up to 36%. So yes, the reaction times are different for some reason, which I find a bit odd. But you can still make some sort of, let's say, hand-waving conclusions from the catalyst activity. The fact of the matter is, scientists do these sorts of things to steer selectivities. this is what I want to show you. Again, it all boils down to selectivity and activity. And remember, we have different types of selectivity, and how do we measure activity? Turnover frequency, turnover number. These are very important things in the realm of catalysis. So before we have our break, let's refresh and revise. What have we learned up until now? We've learned alkene metathesis has got to do with alkenes. It's catalytically promoted. It is like changing dancing partners. It is facilitated. You can do it with a range of systems. Schrock did it with tungsten. Grubbs does it with ruthenium. We have a first generation Grubbs catalyst. We have a second generation Grubbs catalyst. We have a Grubbs Hoveyde catalyst and first and second generation. The idea is that we want to decoordinate the trans-situated phosphine, so an alkene decoordinate. And very important, the mechanism, right, which we looked at in detail. And that whether or not that you can play around with the catalyst conditions to steer it towards ring closing or ring opening metathesis, depending. And you can modulate the catalyst electronically and sterically to steer selectivities, as we see here. So I think what we're going to do, we're going to spend the next hour finishing up alkene metathesis, and next week we're going to do hydroformylation. In other words, for the midterm, it's going to be up until alkene metathesis only. What we're also going to do today is alkyne metathesis, right? And we're going to end off today's lecture by looking at some selected examples of using these catalysts in very important natural product synthesis, which I think is very interesting. I want you to see the power of this system, and let's reconvene in 10 minutes.